Well, my battery died on that last video. Excuse me, that last video. So, I go back and I've got it plugged in now. And we went back and tried to figure out where it died at. So we were talking about the system boundary and the mass that crosses the boundary. Notice, if this is my system boundary, this shaded area here, notice what's crossing the boundary. There's no mass, there's just heat and work, meaning this is a closed system. Okay? This is a closed system, and it's also something we call a cyclic system. A cyclic system means that if I call this state 1, what goes right into the turbine, and it goes all the way around, and it comes out of the boiler, we call that state 2. Notice both of those are this high pressure, high temperature vapor state. What that means is that the U value, right? A cycle means that it's going to return, the system returns to its initial state at the end of the process, meaning that if you start at some initial state and it goes around some process on a pressure volume or temperature volume or any diagram you want to build, it goes through some process and it comes back to that final state which we have here. Water going into the turbine, goes through this process, and it comes out of the boiler ready to go back into the turbine. That's what our process path looks like. This is what we call a cycle. Something important happens when we have a cycle. The change in the energy of my system is equal to 0. Right? So basically we're saying that U1, right, what you're saying there is you're saying that U1 is equal to U2. And the kinetic and potential energy is negligible, or at least not changing either. This entire system is not changing its kinetic energy, it's not changing its potential energy, and if it's a cycle, it's not changing its internal energy. So if the change in the energy of the system for this cycle is 0, meaning it's got the same initial and final U values, right? And here we're saying, well, you apply the first law to this thing. If you apply the first law to this thing, I've got heat in, work out, work in, heat out. And I've got all these terms here, work in, work out, heat out. That's equal to change in the energy of the system. And again, this is equal to U2 minus U1. And if these are the same, then this change is 0. So if this is 0, and if I put the works on one side of the equation and heat's on the other, so I've got heat in minus heat out, I move the work out and the work in to the other side of the equation where the 0 is, because this goes to 0. Saying this is 0. And I can say that the net work out, I'm going to write this down, because this is important. Again, the first law for a heat engine says that the work in plus the heat in minus the work out minus the heat out is equal to 0 because it's a cycle. And we say, well, let's put the heats together. Let's say Q in minus Q out is equal to work out minus work in. And what we do is we can say, well, this is what we call Q net in is equal to W net out. And that's what we're saying here. We're saying that the net work out, that's not on your screen right now, I apologize. We're saying the net work out, the difference between work out and work in, is equal to the difference between heat in and heat out, the Q net in. All right. Now, if we talk about what we call the thermal efficiency, we talk about the thermal efficiency. We introduced the concept of efficiency in Chapter 2, and we said the efficiency is your text loves this concept of output over input. And that's okay. It's not a bad way to look at it. We can simplify a lot of situations to that. It's a lot of times it's what you want out of the device, the process, divided by what you have to put in. So what we call the thermal efficiency sub TH, thermal efficiency of a heat engine is going to be what we want. What we want is the net work output. To get it, we have to put heat in. Right? This is what we're going to sell, and this is what we have to pay for, essentially. Okay? And the thermal efficiency is how good is the device at converting this to that. If it's 50%, if the efficiency is 50%, that means it's converting about 50% of the heat in to net work out that we could possibly sell or make a profit on or generate products that we could sell or benefit other human beings or whatever it is we're going to do with this network out. Okay? Now, notice up here that the network out, which is equal to Q net in or Q in minus Q out. Now, if I substitute this in here and I say, well, this could also be Q in minus Q out based on the first law, that's W net out is equal to this, divided by Q in. And if I divide each of these terms, well, actually I don't have to do anything. I could say this over this is 1, so this is 1 minus this ratio. And so it's not uncommon that we'll write this thermal efficiency as 1 minus Q out over Q in. Now this is going to be important next time when we talk about the performance of ideal devices. The performance as a function of the ratio of the heat transfers is going to be important later on. Okay? But again, this is the thermal efficiency of a heat engine. I can compute it either way and get to the same quantity. And here's one with pretty straightforward numbers, so it's really easy to figure out. Let's say that we've got a device where we're pumping in 100 megajoules and it's kicking out 55 megajoules of net power output. The difference between the work into the pump and the work out of the turbine is 55 megajoules. And so the first law says, well, if you're putting this in and this is coming out, the remainder of this has to go somewhere, and that's going to come out here as Q out. So it's 100 megajoules in, 55 megajoules out of work. That means 45 megajoules has to go out as heat. And if you look at the numbers here, well, if the net work out is 55 and this is 100 in the denominator, 55 over 100 is just 55%. The same as 1 minus this remainder, the Q out, 45 divided by 100. Now notice they're using these subscripts here, L and H. The reason for that, notice they're saying this QH is coming from the high temperature furnace and the QL is going to the low temperature atmosphere. So if we go back here to my drawing a couple pages ago, this heat in is coming from a source at a high temperature. And so rather than Q in, I will normally just simply call this QH. Okay? And this heat out is being rejected to a low temperature sink. That sink is down here at TL. So normally we can call this Q out or QH QL. QL is what we normally call that. So Q out or QL. We'll typically use L and H as my subscripts rather than in and out. H referring to the heat going to or coming from a high temperature reservoir. L referring to the heat going to or coming from a low temperature reservoir. In the case of a heat engine, it's the direction is as we've drawn it there. So this expression here, you can write as 1 minus QL over QH. This is 4. Right? Okay. So it's not uncommon that we'll use those subscripts of H and L. In fact, that's actually common in this text. The high temperature reservoir is going to be labeled H, and the low temperature reservoir is going to be labeled L. Okay. Now, remember our good friend Rudolf Clausius says to us that it is impossible to construct a device operating in a cycle. We've already seen heat engines operate in a cycle. It's impossible to produce a device or construct a device that operates in a cycle and produces no effect other than the transfer of heat from a low temperature body to a high temperature body. However, can you think of a device, any device that you've encountered that pulls heat from a low temperature body and moves it to a higher temperature body? Well, I'm building this video right now in the summer, and I'm going to bet most of you have encountered a device that moves heat from a low temperature body, the inside air of your house or apartment, and it moves that heat to the high temperature body of the outside air. That's an air conditioning system or a refrigerator. An air conditioning system is a refrigerator. It's a type of refrigerator. It's not what we would keep food in. It's not that kind of refrigerator, but it is a refrigeration device. A refrigerator is a device that requires a work input and transfers heat from a low temperature medium to a high temperature medium. Quote from the direct quote with no source means that's a direct quote from your book. The working fluid used in a refrigeration cycle we call a refrigerant. So about anything could be a refrigerant. We could use air as a refrigerant. Some systems will use carbon dioxide. Your standard refrigerants like R134 and R410, those are some kind of fluorocarbon or chloro or fluorocarbon, some kind of hydrocarbon that has some chlorine or some fluorine infused with it, that will go through a phase change, liquid to vapor phase change at favorable pressure temperature combinations to allow us to move heat around and allow it to flow through these devices at pressures and temperatures that are favorable to heat and or cool objects that we normally would like to heat or cool. Okay, so that's what we call refrigerants, but anything that flows through a refrigerator effectively and will move energy through a refrigeration cycle can be called a refrigerant. Now, like I did with the heat engine, I'm going to draw this with you guys. Okay. We'll just set this aside as a separate entity. I'll set this kind of where we can see it. Let's talk about a refrigerator. So a refrigerator, you can start anywhere on the cycle. I'm going to start with the compressor. This text likes to draw the compressor in a piston cylinder format. I understand why they would do that. I don't like to do that. I like to draw the reverse of a turbine. The turbo compressor. Something a little more like a pump. So a compressor is a device that puts work into the fluid. Now, how that manifests itself depends on the fluid flowing through it. In this case, if I've got refrigerant vapor, if I squeeze that down, what happens? Well, think about if you've ever used a bicycle pump, you know, one of the little things that you push the handle and it compresses air into a tire. If you ever used one of those, and if you feel of that, the bottom of that barrel of that compressor, that's a compressor. You're putting work into it, and that's increasing the energy of the flow stream, the air that's moving through it. Now, what happens to the temperature of that bike pump when you get done with it? Or if you've ever had a, one of the little plug-in compressors that you plug in your cigarette lighter in your car, or your 12-volt port, and use that to air up your tire, what happens? Those things get hot, really hot. So what happens is, when you compress a gas through a compressor, it's going to get, how much time I got? You're going to end up with very high temperature, high pressure vapor coming out of that compressor. I'm going to pause there and we'll start the next video.